Hello students, welcome to this video. In this video we're going to go over question 1 from chapter 2. I left that off on the last video. We're going to continue it here. So we have our linear programming problem where we're trying to maximize Z, profit, for this question. We should have this in there. That's our objective function. Maximize Z equals 10 times x1 plus 6 times x2, subject to these two constraints. The two constraints are the amount of flour we have and the amount of time in minutes. So let's first of all, we're going to draw out the constraints, x1 horizontal, x2 vertical axes. And over here we're going to put in values for x1 and x2. So to draw a straight line we need 2 points. We know this is a straight line, so that's all we need. So for this, the easiest way to do it is to substitute in 0 in for one of the variables, solve for the other one. So in this first constraint, if x1 is 0, it means 8x2 is less than or equal to 20. And because we're trying to find the boundary limit, the maximum value, we're going to set that to be equal to 20. So 8x2 equals 20, x2 would equal 2.5 here. Oops, not 2.5. And then we do the same thing, but substituting 0 in for x2. We solve for x1, so in the first constraint, 3x1 plus 0 equals 20. So 20 divided by 3 gives us 6.6 repeating. So we can draw this equation on here. So the first coordinates is when x1 equals 0. So there's 0 for x1, and x2 equals 2.5. I'm going to put 2.5 right about there. Second set of coordinates is when x1 equals 6.6 repeating. I'm going to put it right there. So we don't have to draw this to scale. We are just drawing this so we can get an estimate or an idea of what the boundary is. So we can solve this linear problem graphically. So now we need to connect these 2 points, and sometimes that's the hardest part. Let's look at that. Perfect. And basically the inequality sign tells us that it's less than this. So we cannot produce a value out here. Say that's like maybe 4 x2s and 5 x1. So that would be 5 and 4. Anything beyond this black line here is infeasible. It's impossible. So this we can't do. But anything in here is possible. Anything underneath this boundary line is good. However, because we want to maximize profits, we don't want to produce here, say at 1x1 and 1x2, because we can make more profit if we were to go out to this boundary limit. So let's do the same thing for constraint number 2. We put 0 in for x1, which leaves us 45 times 0 is 0, plus 30x2 equals 180. 180 divided by 30 gives us a value of 6. Then we alternate that one. We set x2 equal to 0. And we're left with 45x1 plus 0 equals 180. So x1 would be 4. So there's our two coordinates for the second line. So when x1 is 0, x2 is 6, way up here. Let's put that up there. And this one is, the second coordinate is when x1 equals 4, which is maybe there, when x2 equals 0. That's why we use 0, because we know where 0 is on the graph. 0 is right on the either x1 or x2 axes. We could use values of when x1 equals 1, what does x2 equal? But then it becomes a little more complicated to draw. So now, let's connect these points. That's not very good, but you get the idea. I'm going to just make that like that. Okay. And so this line, basically, it's telling us that it's less than. This is a time constraint, so it has to be on this side of that boundary line. We can shade in. Everything in here will be feasible. This is where the optimal solution is going to exist, somewhere in the yellow area. Of course, because we want to maximize it, we're going to produce a point. We're going to go right to the boundary limit. So it could be at either A, B, the intersection of those two, or C, down here. Let's change colors. Let's go at point A. Point A and point C, we already know the coordinates. x1 at point A is 0. x2 equals 2.5. So Z would equally put that into this equation. 10 times 0 plus 6 times 2.5. That gives us something like 15. I want to say 15. Now going back to this graph here, this point right in here. This point would be okay for constraint 2, but would not be okay for constraint 1, that first line, the first constraint line that's lower down. This point here would not be good because it has to be feasible or possible for both. So that's point A. We're going to go on to point C, because point C is just as easy. x1 equals 4, it's this point here, and x2 equals 0. So we put that into the objective function. 10 times 4 plus 6 times 0, that gives us 40. I'm going to switch markers here to blue to solve for point B. Point B, a little trickier. We need to substitute in a value. We have two unknowns. We have two equations. So this is something we can do. It just takes a little bit of algebra. So here's the equations. What I'm going to do is rewrite equation 2. 45x1 plus 30x2, and we're going to set this to be equal because we know the solution is on that boundary line. Now I could choose the first constraint if I wanted to, but I just know from looking at that first constraint that I'm going to start with I'm going to be using decimal numbers in here, and I want to stay away from that. So that's why I'm using this constraint, and I'm actually going to solve for x2. So 30x2 equals 180 minus 45x1. Dividing by 30 on both sides gives us what x2 equals, and there is still a decimal there for the coefficient for x1. We can substitute in this value into the other constraint. So 3x1 plus 8x2. 8x2 equals now 6 minus 1.5x1. And that is on the boundary equal to 20. So in this case we have 3x1 plus 48 minus 12x1 equals 20. We want to get all the x's on one side and all the numbers on the other side. So 3x1 minus 12x1 is negative 9x1. And then 20 minus 48 is negative 28. So this gives us x1 value to be 3 1/9. So I'm going to go 3.1 repeating. So we solve for x1. x1 is 3.1. We can take this back to our graph, and we can kind of see that, if we drew this better, we know it's less than 4. So that's a good our graph gives us a good estimate of the value for x1 x1. Now we put this value of x1 into. We always alternate the equations that we're working on. We are working with the first one, 3x1 plus 8x2. Now we put this into the second one, 45 times 3.1 repeating plus 30 x2 equals 180. 45 times 3.1 repeating. If we don't use, if we don't simplify that decimal, we will get an answer of 140 plus 30x2 equals 180. We got 30x2 equal to 40. Divide by x, we divide by 30 on each side, and we're left with x2 equals 1 1/3, 1.3 repeating. So now we know that this value here, point B, is when x2 is 1.3 and x1 is 3.1 repeating. So we can calculate what the objective function would be at that point. So z would equal 10 times 3.1 repeating plus 6 times 1.3 repeating. Z is going to equal 39.1 repeating. Something close to that. That's our z value. Well, note, where is our objective function maximized? It's going to be maximized. Let's turn this green. It's going to be maximized at point C. So that is the optimal solution. x1 equals 4, x2 equals 0. So in order to maximize profits, we would produce 4 x1s and 0 x2s. I think this example has to do with bread and something else. But that is our optimal solution as I've highlighted in green.